Okay, let's continue with our series on simple Haar wavelets. This is part 2, basic Haar wavelet transform. So let's start with a definition of an explanation of the basic Haar wavelet. And you can review the previous part 1 of this series where we have defined some of the terminology, some terms that will be necessary. So psi of from 0 1, which is 0 is included and 1 is excluded, is defined. This is the basic Haar wavelet. Is defined as the difference between phi from 0 to 1 half. 1 over 2, 0 included and 1 over 2 excluded, minus phi from 1 over 2 to 1 over 2 included and 1 excluded. So this is the basic wavelet, Haar wavelet. So let's draw a couple of graphs and see what it actually means. So this is our half the interval, and this is 1. So this is phi from 0 to 1 half, 0 included and 1 half excluded. So this is 1, and okay, this is what this function looks like. So 1 from 0 to 1 half, 1 half is excluded, and from 1 half to positive infinity it's 0, and from 0 to negative infinity, 0 not included, it's 0 also. Okay. Alright, and then let's graph phi from 1 over 2 to 1. So it's this. So it's a step function. And then when we take minus of that step function, so this is phi from 1 over 2 to 1. Okay, and then let's draw the minus, because we have to subtract phi from 1 half to 1 from phi, the step function, from 0 to 1 half. So this is 1, and this will be minus 1. So this will be half. So minus phi, we're drawing minus phi from 1 half to 1. So this will be 0, 0 in this interval, and then minus 1 from 1 half to 1. So this is minus phi from 1 half and 1 from 1 half to 1. So this is the final graph. So on this interval it will be 1, so, and then from 1/2 to 1 it's 0 plus minus 1, so this will be from 1/2 to 1. So this is the psi from 0 to 1. That's the basic wavelet. Okay. So combining two adjacent steps, we are trying to approximate the approximating function, right? It's f tilde from the previous screencast, and f tilde is approximated by combining two adjacent steps into one wider step and one wavelet. Okay, so that's the as we will later discover, this basic combination, right? The representation of two adjacent steps in terms of wider step and one wider step and a wavelet can go on until we only have one wider step and one wavelet, right? So we can have multiple adjacent steps and then keep on repeatedly applying this basic transform to each pair of adjacent steps, and eventually we'll end up with one wide step and one wavelet. So so we considered the basic wavelet, right? We just covered basic wavelet. Now this is the one wider step. So this one wider step is phi from 0 to 1 is equal to phi from 0 to 1/2 plus phi from 1/2 to 1. Okay, so this is what looks like. Okay, so this is phi from 0 to 1/2, and now we're gonna graph phi from 1/2 to 1. Okay, this is what this step function looks like. Okay, so let's sum it up. Okay, so that's one wider step. The sum of two smaller steps is replaced by one wider step. Okay, so let's talk about the sum and difference of two adjacent steps, so that we can derive the formulas of the smaller steps in terms of the wider step and the wavelet. So phi from 0 to 1 is equal to phi from 0 to 1/2. Okay. And then psi from 0 to 1 and then this is the basic wavelet minus phi to from 1/2 to 1. So, and our objective is to derive the formula for smaller steps in terms of the wider step and the wavelet. So let's add phi from 0 to 1 plus psi from 0 to 1 is equal to 2 times phi from 0 to 1/2, right? So if we add the two equations, and so that means that the formula for the smaller step in terms of the wider step, so in other words phi from 0 to 1/2 is equal to phi from 0 to 1 plus psi from 0 to 1 divided by 2. Okay, and then similarly, to get the formula for the phi from 1/2 to 1, we will subtract the two equations. So phi from 0 to 1 minus psi from 0 to 1 is equal to 2 times phi from 1/2 to 1 So some algebra here, phi from 1/2 to 1 is equal to the difference of phi from 0 to 1 minus psi from 0 to 1 divided by 2. So what we did was we derived formulas for two smaller steps in terms of the formulas, in terms of the wider step and the wavelet. So two narrower steps. Okay, so let's try to graph what we just did. So phi of from 0 to 1/2, the step function, as we just derived, is phi equals phi from 0 to 1 plus psi from 0 to 1 divided by 2. Okay, that was the first formula, and then the second formula that we derived was for the second half of the step function, for the second half of the interval. 5 from 1/2 to 1, 1/2 included, and 1 excluded. So we are using the notation defined in the textbook Wavelets made easy. So and this is equal to 5 from 0 to 1 minus psi from 0 to 1 divided by 2. So this is 5 from 0 to 1. And half of that is just going to be the step function where the height of the horizontal line will be at 1/2. Right, if we multiply that step function by 1/2 uniformly on all of the intervals, then the step function will look like this. So 1/2, right, and then from 0 to negative infinity, 0 excluded, it'll be 0, and the one from positive infinity, 1 included, it'll be also 0. Right, and then minus psi, right, from 0 to 1. The basic wavelet is gonna look like this, right? This 1, right, and then minus 1 here, and then 0, 0 here. Right, so if you if we do half of that, right, so then it'll be half on the interval from 1 to 1/2, 1 included, 1/2 excluded, and minus 1/2 on the interval from 1/2 included to 1 excluded. Okay, so when we add that, right, so we're gonna get half plus half on that interval will give us 1. Okay, this is half, this is 1. Let me grab the red color. So half and half will give us 1. And then half plus minus half will give us 0. So this is what the smaller step formula looks like in terms of the wider step and the basic wavelet, the first smallest step, right? And it's important because once we have the wider steps, right, we can recover the smaller steps if necessary. So we're not losing any information, which will become very important to us once we actually start implementing the Haar Wavelet algorithms. Okay, so half of that will be excuse me, this, the step function. Okay, and that's 0 here and 0 here. And then we need to do minus the wavelet. And the basic wavelet, notice that the basic wavelet changes by the absolute value of 2, right, from 1 to -1. Not important for now, but again, it will be later. So this is the basic wavelet, and we need to multiply it by 1/2, which will reduce it to 1/2 from 1 included to 1/2 excluded, and minus 1/2 from 1/2 included to 1 excluded. Okay, so minus the upper graph minus the lower graph, so this will give us 0 on from 0 to 1/2, and then half minus half will give us 1 on the interval from 1/2 to 1. Okay, well, this is to end 0 here. Okay, well, this is to be continued, and thank you for watching.